Imagine standing under a night sky, gazing at what seems like countless stars. For centuries, humanity looked up and wondered, are there other worlds out there, orbiting those distant suns? Worlds like ours, perhaps even teeming with life? This question, once confined to the realms of science fiction, is now at the forefront of astronomical research. Yet, the reality of finding these alien worlds, known as exoplanets, is not a dramatic, high-speed chase or a sudden discovery of glittering civilizations. Instead, it's a meticulous, long, and often incredibly boring process of patient observation, subtle data analysis, and the quiet, persistent search for the most elusive of cosmic truths. It's the ultimate cosmic detective story, played out over light years, relying on the mundane wobble of stars and the faint dimming of distant light. Okay, so dim the lights, perhaps turn on a fan for that soft hum, and let's ease into tonight's journey together. Last time, we delved into the universe's most enigmatic components, dark matter and dark energy. We learned that the vast majority of our cosmos is made of unseen stuff, a silent, invisible scaffolding holding galaxies together, and a mysterious force accelerating the universe's expansion. Tonight, we move from the unseen forces of the cosmos to the unseen worlds around distant stars. For most of human history, the only planets we knew were the ones in our own solar system. Those familiar worlds we toured a few episodes back, orbiting our single sun. The idea of planets orbiting other stars was pure speculation. It's delightful to imagine, but impossible to prove. The sheer distances involved make it incredibly difficult to see these faint, tiny worlds next to their blindingly bright parent stars. It's like trying to spot a firefly fluttering around a distant lighthouse from hundreds of miles away. But in the last few decades, through incredibly patient and persistent scientific effort, we have transformed this speculation into a vibrant field of study. We've discovered thousands of exoplanets, quiet witnesses to the fact that our solar system is not unique, and that planets are, in fact, a boringly common byproduct of star formation across the galaxy. So, how do astronomers find these incredibly distant, often tiny worlds? It's rarely by simply looking through a telescope and seeing them directly. That's because the light from their host star is billions of times brighter, utterly swamping any light reflected by a planet. Instead, astronomers rely on incredibly clever, often subtle, and utterly boring indirect methods. These methods exploit the mundane laws of physics and the predictable interactions between stars and their orbiting planets. One of the most successful methods is the transit method. Imagine you're watching a distant star. If a planet happens to pass directly in front of that star from our line of sight, it will block a tiny fraction of the star's light. This causes a very slight, temporary dip in the star's observed brightness. This dip is incredibly small, often less than 1% of the star's total light, and it's a perfectly normal, boring event. The Kepler Space Telescope, for example, spent years staring at a single patch of sky, patiently monitoring the brightness of over 150,000 stars, waiting for these subtle, repetitive dips. The periodicity of these dips tells us the orbital period of the planet, and the size of the dip tells us the size of the planet relative to the star. It's like watching a distant streetlight and noticing a minuscule, repetitive flicker when a tiny insect flies across its beam. This method has discovered the vast majority of known exoplanets, all through the boring, consistent measurement of stellar brightness over long periods. Another powerful technique is the radial velocity method, also known as the Doppler wobble method. This method relies on the gravitational tug-of-war between a star and its orbiting planet. Just as a planet orbits a star, the star itself is also slightly tugged by the planet's gravity, causing it to wobble ever so slightly around a common center of mass. This wobble is tiny, often imperceptible to the naked eye, but it causes the star to move slightly towards us and then slightly away from us. When a star moves towards us, its light waves are compressed, shifting slightly towards the blue end of the spectrum. When it moves away, its light waves are stretched, shifting towards the red end. This is the familiar Doppler effect, which applies to sound, but also to light. By meticulously measuring these minuscule, repetitive shifts in the star's light spectrum, astronomers can infer the presence of an orbiting planet and even estimate its mass. It's a very precise, very boring form of stellar spectroscopy, measuring tiny shifts that occur over days, weeks, or years. This method was responsible for the first confirmed exoplanet discovery around a Sun-like star, 51 Pegasi P, back in 1995. A less common but visually fascinating method is direct imaging. As the name suggests, this is literally taking a picture of the exoplanet. This is incredibly difficult because, as mentioned, the star is overwhelmingly bright. To achieve this, astronomers use special instruments called coronagraphs to block out the star's blinding light, much like using your hand to block the sun's glare so you can see something next to it. They also use adaptive optics to correct for the blurring effects of Earth's atmosphere. Even then, the planet usually appears as a tiny, faint speck of light, billions of times dimmer than its star. It's not a crisp, colorful image like Earth from space. It's often a single pixel, slowly orbiting its star. This method mostly works for very large planets that are very far from their stars. It's beautiful but rare, and the resulting images, while profound, are often visually quite boring, just a faint dot. Other, even more arcane methods include microlensing, where a foreground star and its planet temporarily magnify the light of a background star as they pass in front of it, and astrometry, which involves precisely measuring the tiny, boring side-to-side wobble of a star on the sky due to a planet's gravitational pull. All these methods are variations on a theme, observing the incredibly subtle, predictable effects of a planet's gravity or a presence on its host star's light or motion. So, what have we found with all this boring, meticulous work? As of today, we've confirmed the existence of over 5,000 exoplanets, with thousands more candidate planets awaiting confirmation, with years lasting just a few Earth days. It's not very exciting for life, but common. And the boring truth is, exoplanets are incredibly diverse. We found hot Jupiters, gas giants orbiting incredibly close to their stars. Super-Earths, planets larger than Earth, but smaller than Neptune, a type of planet not found in our solar system. Some might have rocky surfaces, mini-Neptunes, smaller versions of ice giants, also common, ocean worlds, planets thought to be covered entirely by deep oceans, and, most excitingly, for the search for life, a growing number of potentially habitable exoplanets, worlds roughly Earth's, orbiting within their star's habitable zone, where temperatures might allow for liquid water on the surface. These are the Goldilocks planets, just like our Earth, not too hot, not too cold. This requires incredibly powerful next-generation telescopes like the James Webb Space Telescope, capable of analyzing the faint light that has passed through an exoplanet's atmosphere. The analysis of these light spectra is painstakingly slow, highly technical, and for most, incredibly boring. It's looking for the faint chemical fingerprints of distant worlds. The sheer abundance of exoplanets, now known to outnumber the stars in our galaxy, changes our perspective on humanity's place in the cosmos. Our solar system, once thought to be unique, is now just one among billions. This boring ubiquity of planets suggests that the conditions for life, at least simple life, might be far more common than previously imagined. It's a profound shift in our understanding, born from the mundane observation of distant stellar wobbles and dimmings. So, the next time you look up at a star, remember that it's likely not alone. It's probably orbited by planets, worlds as diverse and fascinating as those in our own solar system, perhaps even some quietly harboring life. The search for these exoplanets is a testament to the power of patient, indirect observation, relying on the predictable laws of physics and the subtle whispers of distant light. It's a truly boring, yet profoundly hopeful endeavor that continues to redefine our place in the vast, quiet universe. Next time on Boring Astronomy, we'll contemplate the ultimate cosmic finale, the end of the universe. Cosmic doomsday scenarios explained. We'll explore the quiet, inevitable fates that await our cosmos, from the slow cooling of a big freeze to the eventual disappearance of stars and galaxies.